So for cyclic hardening material, where my stress increases in each cycle, the cyclic stress strain diagram will look like this. So what is happening in this case is we are keeping the strain constant in each cycle, okay? And this is my strain axis, this is my stress axis. So let us keep, first of all, the strain values which are going to be constant. So this is my epsilon max which I am applying in tension, and then I am applying epsilon minimum in compression. So mod of epsilon max is equal to mod of epsilon min. The sign is different because the R ratio is 1 and sigma mean is 0. Sorry, epsilon mean is 0 in this case. So if it is cyclically hardening, you will have something like this. So you will have initially linear elastic, and then the material will deform plastically, right? And then you will unload it, and it will unload, and then in the next cycle, so in the next cycle it will deform at a later stage and it will go to that strain value, and then in the next cycle again, so you are unloading again, so it will follow the same slope, and then in the next cycle for the same amount of strain the material will deform to a different stress. Okay, so the yield strength is there, and then it goes to a different stress. Then you unload it, then it goes back to same strain value. So this is my first peak, this is my second peak, this is my third peak, and so fourth peak should go more than third and also 2. So this is wrong. So it will go something like this. Okay, and so it will reach epsilon minimum, and then you unload it, and then it will go to another higher value, and it will come back to another higher value, and so on. Okay, so you see in each cycle what is happening is that this loop is increasing in this direction and decreasing in this direction, right? So for the same amount of strain you will have to apply more force on the material, okay, to have the same amount of strain in the material, and this is cyclic hardening. Opposite will happen in cyclic softening. So let me extend this part, and we have stress and we have strain, and we again fix the amplitude of strain. So this is my epsilon max, this is my epsilon min, okay, and in this case what do we have? So in the first cycle you will have, let's say it goes to that strain, okay, so this is my first peak. In the second one it will go to a lower value of stress, okay, so it will go somewhere here, and this one is, so this is second peak, okay. In the next one, so you unload it, it goes to the same slope, and in the next one it goes to a smaller value of stress, okay, and then you unload it, and then it goes to a further smaller value of stress, then you unload it, then it goes to a further smaller value of stress, and so on. So this is how it will look like in cyclic softening. So this is softening and this is hardening. Okay, so this is how the material will evolve with each cycle. So what happens is, like, if we have to find out the stress strain behavior of the material, then in each cycle the hardening or softening will define how the material is getting hardened or softened in cyclic mode of loading, which will be different from monotonic loading. So in order to find out the cyclic stress hardening and stress softening curve, it's a little complicated, and it is also dependent upon the behavior of the material. So what happens is, this change in loop will stabilize after some time. Okay, so this hardening, so we have reached 3 reversals, so 3 peaks, and then if you keep on doing this, the material will be reaching the same value over and over again. Okay, so it will keep on repeating the same value. So what happens is, the material stabilizes. Okay, it is similar to what you have in monotonic loading. So it increases linearly, and then you have non-linear. So stress is increasing, right? And then you reach UTS, where beyond which the material is not getting hardened anymore, but it starts to fail. It starts to damage. So this is the saturation point. Beyond this, hardening is not going to happen, right? But it is not exactly this what is happening in cyclic loading, but you can imagine it in analogy to this one. So what happens is, this hardening behavior, the material gets hardened, but after some times it cannot harden further, and similarly in softening material it cannot soften further. So of course a metal can not keep on softening and become something like a plastic, a molten plastic or something, or a molten glass. So it can only get softened to certain limit, and after that it is not going to soften further, right? So that's where the material gets saturated, and then beyond that there is no further softening or hardening. So what we do is, we do the testing at different amount of strain values, at different amount of constant strain values. Okay, and we do this cyclic loading. So for instance, we do so we are keeping R is equal to 1 for all the tests, and we keep epsilon max. So epsilon mod of epsilon max is equal to mod of epsilon min. That's the kind of cycle we are applying. And then what we do is, we define a value to it. So let's say 0.5 in, but 0.5 will be too high. So you can imagine it to be 0.1, let's say. So we do the first testing at 0.1, then we do the second testing at 0.2, we do the third testing at 0.3, and so on. Okay. So we do the testing at different values of strains, and we let the cyclic loading, we allow the cyclic loading till the point this loop stabilizes. Okay. So it stabilizes usually it stabilizes after 100 number of cycles. Okay. So after 100 number of cycles, you will not see this fluctuation in the cyclic stress strain behavior. So once it has stabilized, then we take that stabilized value, okay, for each value of strain, and we plot that. So if you plot that, then it will look like this. So this is again my strain value, strain axis, this is my stress axis, and what I have done is, I have taken different stabilized hysteresis loops for different amount of strain. So this is shifted from the axis. It should have been, so the y-axis should have been at the center. Okay. So imagine that the y-axis is going from the center, because my R is 1. So this is the first, so this is for this one, okay, and this is the loop which has stabilized. So after this there is no hardening and softening. Then I take another loop for 0.2 of strain value. So of course that will be bigger than this, because I'm going higher in strain, and now I'm plotting something for cyclically hardening material. Okay, so of course the stress will be higher. So this is my second loop. Then I do the same thing for third value of strain, and I plot it. So forget about the lower part, it is going to be like that, and then we do it for the fourth value, and similarly you will be getting this kind of plots. So once you have plotted all those, then you select these points, okay, and you join these points, and that becomes your cyclic stress strain curve. Okay, so this is your cyclic stress strain curve. Of course you can decrease the value of strain and have smaller and smaller loops, okay, and you can join those to make the initial part. So it starts from the center, and so this will be your cyclic stress strain curve. Okay, so this is my cyclic stress strain curve, and if you compare it with the monotonic stress strain curve for cyclically hardening material, then the monotonic curve may be something like this. Okay, so this one, and the cyclic hardening curve will be higher than this because the material is getting hardened. Okay, so there is a difference in what you get from monotonic loading and what you get from cyclic loading. So this is the way by which the cyclic stress strain curve is obtained, and after getting that we can again define a similar equation what we did in elastic plastic material, where we defined sigma is equal to k into epsilon to the power n for the non-linear part of the stress strain curve in monotonic loading, right. Similarly we can do something like delta sigma is equal to some constant, let's say k dash, into delta epsilon plastic to the power n. Okay, because of course we are talking about non-linear part, which is only plastic strain, we are not talking about elastic strain. Okay, so we can have a similar equation in cyclic loading also. So we can have a power law relationship. Apart from this, if you break the total strain as we have done earlier, so the total strain, or the total is half of the strain, so this is half of my complete cycle, right. So if this is, let's say, my strain cycle, so I am going to this strain and then I am going to that strain, so this is my half strain, right. So total delta epsilon is this, right. This value is delta epsilon, and this value, if we keep this value and this value constant, so this is obviously half of delta epsilon, right. So we take half of delta epsilon, and this delta epsilon is a part of elastic strain and plastic strain, right. So we can break it like this, and then for the elastic part again we can apply Hooke's law. So we can replace delta epsilon elastic, so elastic, with delta sigma divided by E, which is the Young's modulus. Okay, so if you use this and plug it in here, then you get delta sigma divided by E, and 2 will come, plus delta epsilon plastic divided by 2, and this you can replace from there. So finally you get delta epsilon by 2 equals delta sigma by 2 into E, plus now delta epsilon P is equal to delta sigma divided by k dash to the power 1 by n, right, and 2 will remain outside. So 1 by 2 into delta sigma divided by k dash to the power 1 by n. Okay. So, this will be your constitutive equation, your stress strain relationship for cyclic loading. Okay. So, if you plot the SN diagram, so this is your, so you can plot sigma max or you can plot delta sigma. Okay. So, you can plot, let us say sigma, let us say we plot anything. So, either delta sigma or sigma max, does not matter. We are talking about a general diagram, and here we have number of cycles in log. So, we get this kind of curve. Okay. So, this is my endurance limit and there is this transition. So, usually what happens is that the study on fatigue started with in this range. So, somewhere here. Okay. So, where the stresses are not very high. Stresses are usually in this case lower than yield strength. Okay. So, what happens is you only have elastic deformation, and people thought that material will not fail because the stresses are not beyond yield strength. So, there is no reason for the material to get any damage and it should not fail then, but material kept on failing, and especially that happened in the cyclic loading condition. So, researchers did this analysis and they found that even if the stress is lower than yield strength, the material still can fail, especially when the material is having or undergoing cyclic loading. So, this research was mostly for 10 to the power, so for cycles more than 10 to the power 4. Okay. So, 10,000 or more number of cycles will fail, for example, ball bearings in the cycles or in the shafts, and that is because there is a cyclic loading involved, and people investigated that, and that usually happened at higher number of cycle and lower amount of stress. So, that area is called high cycle fatigue, where you have a comparatively higher cycle. Of course, we are reaching endurance limit, so it does not matter, the whole range can be here, but you have arrived to endurance limit here only, but you will not know that this is the endurance limit unless